So today we want to conclude the initial area and talk a little bit about information theory and complexity theory. So the first part about information theory is the whole study, a large contribution by Claude Shannon. And the fundamental idea is that of unconditional security, something that we have already mentioned but not explored fully. So of course we've mentioned the idea of computational security before, and therefore in that case what we are considering is the difficulty of breaking a system constrained to certain resources. When we talk about unconditional security, we assume that no bounds are put on the resources. So what we will develop is this, and in particular we will develop the idea of perfect secrecy. And the idea of perfect secrecy relates pretty much to the ciphers, and it captures the concept of not revealing any information. So essentially, if we intercept a ciphertext, then there is no information about the underlying plaintext and any future encrypted messages. Come on in. Sorry. I just started introducing the topic.
Oh, okay.
You didn't miss anything.
Cool.
Yes, so the first thing that we want to talk about today is so a little bit of information theory. Yes, and I was just introducing the idea of perfect secrecy.
Okay.
Okay, so basically the probability that we kind of recalled or introduced up to now will come very helpful when looking at this. If you think that, for example, you can define random variables M, C, and K associated with the plaintext, the ciphertext, and the key, so we just determine some random variables. Then we can compute the associated density functions. Remember the Fm, Fc, and Fk.
Mm-hmm.
And also the joint density and conditional density, for example, F Cm of Cm and the F C given M of C given M. Right, so what's the probability that a certain ciphertext is C, given that a certain, that's given that a certain plaintext is M, and so on, okay? For example, the last one is exactly the probability of a certain ciphertext taking a certain value given that the message is M, okay? So how do we define perfect secrecy? Now we have the tools. We say that this system is perfectly secret if f of m given c is equal to f of m. Right? This helps us formalize the idea of perfect secrecy. And this has to be valid for all m in the message space and for all c in the ciphertext space. Okay? So if the probability of any given plaintext is the same as the plaintext given the ciphertext, then essentially the ciphertext is, sorry, the plaintext is independent of the ciphertext.
Mm-hmm.
If it is independent, then it reveals no information, essentially. Now if you use Bayes' formula, we can actually write that f of m given c times f of c is equal to f of c given m times f of m, right? And in particular, we see that with this and this together, we have an equivalent definition, which is that f of c given m is equal to f of c. Okay? And this is formalizing a different thing. It's saying that basically every ciphertext has the same probability of occurring, regardless of the message. Okay? Independently from the plaintext. Now, of course, if we're talking about ciphers, once we know f of k and f of m, then we can determine f of c, right?
Mm-hmm.
Which is again the distribution, the density of the ciphertext. And so what we can do is know that given a certain key, the probability that the ciphertext equals a certain c is the same probability as that the decryption of the ciphertext is the plaintext. Okay, so that's why they are tied together. So we can actually sum over all possible keys, right? And then compute this probability. So what is f c of a certain ciphertext, right, is the sum over f key of a certain key times f m of the decryption of c. Okay, and we sum over all possible keys. Yes?
Yeah.
Because that is the density of a certain key times the probability that that ciphertext decrypts exactly to that message.
Okay.
Okay. So in a lot of cases, this idea seems normal. We just choose everything at random, right? But we can see, for example, here there is a rather artificial example that illustrates why this is not always the case. So let's take a really dumb crypto system, okay, that has exactly two keys, two possible keys, like say K1 and K2, right, and three possible messages, M1, M2, M3, okay? So I can encrypt whatever, 0, 1, and -1, or whatever, okay? I have like three possible messages and two possible keys. Of course, this is a cipher, so I can have also like three possible ciphertext, C1, C2, and C3, okay? So that's my key space, that's my message space, that's my ciphertext space, okay? Now assume that all of these don't happen with the same probability, and of course this is like more realistic for certain things, less realistic for other things. For example, certain messages for sure don't have the same probability of appearing at certain other messages. For the ciphertext and keys, it's a little bit different. But so suppose, for example, that fm of m1 is the same as fm of m2, and they appear with probability 1/4. Whereas fm of m3 is 1/2. Okay, so m3 is much more likely to appear. And then you can imagine, again, for example, that the way the crypto system interacts is this way. If you take m1, m2, m3, you can even use a little table in this case because there's such few elements, right? If you use the first key, so encryption under K1 of M1 gives you C2. Encryption under, so this is like the encryption, decryption, right? If you use the key K1 on M2, you get C1, and here you get C3. And if you use K2, you get C1, C3, and C2. Okay, so it's a very artificial example. Suppose that like I can map exactly, think a shift cipher or something like that,
right,
but with these unbalanced probabilities. Then, for example, if I encrypt, so if I encrypt M1 with the key K1, I get C2, and so on. So if all the keys are used with the same probability now, because this is unbalanced, and because of this distribution here, we can actually compute the probability that a certain ciphertext C1 appears, right? and this is going to be f of the first key times the distribution, or density actually, that the decryption on the K1 is C1, yes, plus the same for the second key, so that's Fm decryption on the K2 of C1. Okay, and so what is this one? This is f of K1, and this is what's the decryption of C1 under the first key is M2, so Fm of M2.
Can you slide it up?
Yep. And then this is f of K2, and the decryption on the K2 of C1 is M1, right?
Mm-hmm.
And now we can actually use our numbers and see that this gives me exactly 1/2 times 1/4 plus 1/2 times 1/4, which is equal to 1/4. Okay, because the keys are equally distributed, they both come with 1/2, and this is 1/4 and this is 1/4.
Mm-hmm.
So, on the other hand, for example, what we can see is that f of C1 given M3 is actually 0. This is M3, of course. Okay? So, you already see that the crypto system doesn't have perfect secrecy because it is not true that we have f of C given M equal f of C.
Right.
Right? It's going to have f of C given M3 is 0, but f of C in general is 1/4.
Mm-hmm.
Right?
Yep.
And this is to be valid for all messages and all ciphertexts. So
Yep.
clearly the distribution is not balanced. Okay? And this is translating to the fact that you can extrapolate something. If you see this ciphertext is much more likely to come from that message, or having used that key, or there's any sort of information that comes out of it.
Right.
Okay? So of course, one condition that we must have always is that the number of ciphertexts, or the cardinality of the ciphertext space, needs to be able to be at least the same as the number of plain texts, right? Otherwise, we cannot uniquely decrypt or safely decrypt, if you want. But to this, we're going to add also another condition. That is, if a crypto system has perfect secrecy, then you also need to have the number of keys, so the cardinality of the key space has to be at least the same as the cardinality of the message space. Okay? And it's not hard to see this. We can see basically that the condition, so for perfect secrecy, we have to have this condition. And imagine if I consider f of C given M, this has to be equal to f of C, and has to be positive for all messages, right?
Mm-hmm.
Because if it is 0 for even just one message, then it's not balanced.
Yep.
Right? And so there is at least a possible probability that M encrypts to C, and so there must be at least one key that satisfies this, for which M encrypts to C.
Mm-hmm.
And if we start with a different M, if we start with an M prime, then we get a different key K prime, because otherwise we would have that the encryption under the key K of M is equal to C, which is the encryption under the key K prime, under the key K of M prime, and then we, this is not one-to-one anymore. This is not a good encryption algorithm anymore.
Yeah.
And so basically, we have to have a non-empty set of keys such that for each message I get a certain ciphertext, and all these sets are disjoints, and so each plain text is matched with one or more keys. So to each message, at least one key. And so there are at least as many keys as plain texts.
Mm-hmm.
Okay? It's very informal proof. But basically, when you consider the union of these two conditions, I need to have at least as many ciphertexts and that I have messages, and also as many keys as I have messages. The simplest way to characterize perfect secrecy is the following one. Think about how to put this together. If I have, this is a theorem by Shannon, right? The number of keys equal to numbers of plain text equal to number of ciphertext, then the system has perfect secrecy. If, and in fact is if and only if, okay? There's two conditions that need to be verified. The probability of each key, let's write it informally, is the same. Okay, so each key is used with equal probability. And then, now I have, look, exactly the same number of keys, plain text and ciphertext. Then, given message M and ciphertext C, there is exactly one key K such that the encryption of K of M equals C. Okay, so a condition, if I have the condition that all my spaces are equal, or at least I have as many, okay, same number, then I want the key, each key to be used with the same probability and to be exactly a one-to-one match between ciphertext and plain text and keys. Okay, in that case, then I can prove that I achieve perfect secrecy. Okay, so this is not hard to prove, but it's a little bit long, and you have it on the book. We're going to skip this proof. But it's very intuitive, right? Because at this point, I have as many keys as plaintext and ciphertext, and I use all of them with the same probability, and exactly one key matches this plaintext to this ciphertext. And so clearly, this doesn't reveal any information, right? So you can make a very detailed argument about this. But what is this leading to then? Because obviously, I have to have at least as many keys as plaintext and ciphertext. So we already mentioned, if you want the most quintessential, if you want, perfectly secret cipher, which is the one-time pad.
Oh, right. Yeah.
When you think about the one-time pad, right, you have exactly the key, which is K0, K1, let's say Kn, and then same messages and ciphertext are of the same length, they're all binary strings, and you just encrypt by doing Ci is Ki XOR Mi, right? And then you can clearly see that if every key is used with the same probability, then there is exactly one binary string that takes this binary string into that binary string, right? Is binary operations XORs. Of course, the key needs to be used just one time because the structure is very simple. It's an XOR, so if the same key is used more than once, then you can cancel it out and you can get some correlation and things. But as long as the key is used only once, then when you see a ciphertext at an intuitive level, this could come from any plain text, because given that ciphertext, you have exactly one plain text for each key. So you have absolutely no information what key was used. Right? So seeing the ciphertext doesn't tell you anything. Or if you want, the ciphertext has the same probability of being every message.
Yeah.
Okay. Of course, we already discussed the idea that the one-time pad is not exactly practical, because exactly you have to have this length of the key, which is the same. There's two problems, right? First is that the key has to be used only once, and then that the length is the same as the message. Okay. So, but at least this kind of formalizes a little bit to the information theory. So, in practice, what happens is that we cannot expect crypto systems to be perfectly secure, and this is why we fall back on computationally secure crypto systems instead. Okay, so this is kind of where we started, in fact, by saying I'm constrained to a certain number of resources. but we kind of want to do a little bit more. So Shannon not only looked at information theory in a number of different areas, but also formalized. So so Shannon was a huge mathematician, and he studied obviously not just things related to cryptography, but about communication theory as well, and codes and other things. He introduced this idea of entropy, which is not exactly the same entropy that you have in physics or dynamical systems or other things, but it also kind of recalls that, because it's just a measure of uncertainty, right? And so that's why I introduced the idea of entropy, because we cannot expect to have a perfectly secure crypto system. So we want to measure now, if I have a crypto system which is not perfectly secure, what is the uncertainty in my ciphertext and plaintext, right? And so yeah, so this way we can quantify. This. So let's use again random variables, right? And obviously, if we have a certain random variable with a certain number of events, and possibly outcome, so possible outcomes are like x1, x2, say xn, and each of them takes a certain probability of happening, like p1, p2, pn. We set pi to be exactly fx of xi, which is, in other words, the probability that x is equal to xi. Yes, like we always do. So we have a bunch of different outcomes, each of them happening with their own probability. It's easy to use random variables, you just have nice notation. So what is the entropy then? It's a function h of the random variable x. This is in general, right? So of course, what we introduced before, we have random variables for keys, for ciphertext, and for plaintexts. But we're just defining the entropy in general. And this entropy should depend only on the probabilities of the possible outcomes. So this is really a function of P1 to Pn. Okay, so if this function is to capture the uncertainty, in other words, we want this to kind of be the expected value, right, of my random variable. If my random variable measures like the uncertainty of the outcome x1, x2, xn, okay? So it kind of measures basically the amount of information that is measured, that is revealed about x. Okay, so there is three properties that we need to properly measure uncertainty, and the first one is that h should be continuous in the pi. Remember that we can really think of these pi's as like variables. This is like a multivariable function, and it should be continuous in this function, which means in an intuitive level that if you change the pi just a little bit, then the expected number, there should be also a small change in the amount of information revealed by x. Okay. So you don't have like big jumps or anything.
Right.
Yes. So yeah. So that's the first property, which is very intuitive. So if you have a small change in probability in one of the pi's, then there should be a proportionally small change in the amount of information revealed. Right. And then the second, suppose now that I have one specific random variable xn, which is uniformly distributed over x1, xn, right? So if this variable has exactly n different outcomes and is uniformly distributed, remember we said that this means that every outcome happens with the same probability, right? So all of the pi's are equal to 1 over n in particular, and therefore what should happen is that the entropy of this random variable should be a monotonically increasing function, right, of n. And what does this mean? It means that basically if I have a certain number of outcomes and they're all equally likely, then my uncertainty increases with the number of events, right? If I have only 2 events, both happen with probability 1/2, it's not very uncertain, right? It's one or the other, but the more events I have, the less I know about which one occurred. Okay, so these two are kind of abstract but intuitive, because the first one is saying that the uncertainty changes kind of proportionally to the probabilities, and then this one captures the idea that if all the events are equally likely, then my uncertainty depends just on the number of events and increases with the number of events. Now the property 3 is a little bit less straightforward, but it's important. So if we have my random variable x, and we have an outcome, say xi, and if we can break it into 2 successive choices, so we have a choice x, and we break it into like a choice y plus a choice z, essentially, right? Then the original value of the entropy, then value of h, should be a weighted sum of the value on h on these 2 successive choices. Okay, so what we can write, if my variable, in particular, the easy case is if my random variable is uniformly distributed, say x n to the r, then this should be r h x n. Okay, if I imagine that I take r repetitions of my experiment, then the uncertainty should be exactly r times the uncertainty of the individual one.
Right.
This is because they're all uniformly distributed. If they are not, then you assign different weights to each branch, essentially. So we can actually make a simple example of this, which I think will be good, right? So suppose that we have my random variable x, and it can take 3 outcomes, x1, x2, x3, okay? And for example, these outcomes are distributed. The first one is x1, second one is x2, third one is x3. This one happens to probability 1/2, this with probability 1/3, and this with probability 1/6. Okay? So the sum is 1, as we know. Okay, good. Now, if I can do, so this is my x, but imagine that I do this as 2 successive choices instead of just like the one choice, right? So instead of like choosing between x1, x2, x3, I can actually do first, for example, a choice between x1 and the other 2. And then if I choose one of the other 2, then I choose between x2 and x3, right? So I can actually change this diagram to something like this. I either get x1 or I get, say, y1, which is one of the other 2. And then I have a certain probability of getting x2 and a certain probability of getting x3. Okay? So this may be a more realistic model than this model here.
Yeah.
In certain situations.
Right.
Now, of course, the probability of getting x1 is the same. Right? And then you have 1/2 for getting the other one. And now I have to split this probability here. Then, of course, you want this to be 2/3 and you want this to be 1/3, right?
Yeah.
For the thing to match.
Right.
So now what happens if I take the entropy, right? So here I have x, and I've split x into a y branch, which is like this part, and then a z branch, which is this part, right? So I split x into y followed by z. This is not like a rigorous plus, but it's like y and then z. Right. So essentially, we have the probability of y be equal to x1 is 1/2, and the probability of y given to y1 is also equal to 1/2. And z depends on y. And in particular, what we have is that the probability of z being equal to x2, given that y is equal to y1, the y is equal to x1. Let's do this one first. This is 0. Right? I cannot get x2 if I choose the first branch. And equally, the probability of z being equal to x3, given that y is equal to x1, is also 0. And the probability of z being equal to x2, given that y is equal to y1, is 2/3. And the probability of z being equal to x3, given that y is equal to y1, is 1/3. Okay, so we've got these informations. And so the property 3 of entropy is basically capturing this. If I have the entropy of 1/2, 1/3, 1/6, which is the entropy of the original random variable, then this has to be equal to the entropy of 1/2, 1/2, which is the y, plus 1/2, because it's, this only occurs 1/2 of the times.
Right.
The entropy of 2/3, 1/3. Okay? And so your function is to be malleable to verify this condition.
Yeah.
Okay? So the uncertainty in the first experiment, where you have like 1/2 of getting the first one, 1/3 of getting the second one, and 1/6 of getting the third one, should be the same as this entropy here, which is calculated in a different way, but if you look at the probabilities, in the end they are the same. Right? So this shouldn't depend on the way you conduct the experiment, but just on the probabilities, essentially.
Right.
But of course, that's why we have a property, because we can calculate in two ways. This is the first experiment, and this is the second experiment, and the two ways needs to bring it to the same place, otherwise there will be something wrong.
Yeah.
Okay. So this captures these three properties, capture the idea of entropy. And what is interesting is that Shannon proved that essentially the only functions that satisfy these two properties, these three properties, are of the form negative, the sum of pi log pi. Okay, this is log 2. Okay. Or multiples of this, constant multiples of this, which again is probably not necessary, right? We have to put a caveat, because of course some events could happen with probability 0. So if I do get 0, then what is log 0, right? So we actually set p log p equals 0 if p is equal to 0. Okay, so this is the generic form for the entropy function. It's easy to remember. It's minus the sum of p log p for all the p's. Cool. And these are the only possible entropy functions up to a certain constant factor, which again we can ignore safely. All right, because then it just scales everything. Cool.
Yeah.
So this clearly verifies the three properties. The proof is not reported here, but it's not hard to see. So, for example, what happens if, say, we have the trivial event in which all the probabilities are 0 except for one of them that has probability 1? Because remember, again, the sum needs to be 1. So if my event is exactly one outcome with probability 1 and every other outcome is impossible, then what kind of event is this? It's a certain event. And so what happens is that I have p log p is always 0 for all the probabilities except the one for which pi is 1. But then again, 1 times log 1. What's log 1? Again, it's 0.
Yeah.
So then the sum is 0. And this makes sense because entropy is measuring the uncertainty. So if this is my experiment, exactly one outcome can happen and the other ones cannot happen, then I have uncertainty exactly equal to 0.
Right.
Okay. And you can also then kind of like look at the other case, what is the most uncertain event? And of course, you can expect that happens when all the probabilities pi are equal, right? So the proof requires a little bit more than what we are willing to look at now, because you have to talk about concavity and other stuff. But basically, what you can show is that the entropy of X is always less than log 2 of n, where n is the number of different outcomes, and it's also actually equal to log 2 of n if and only if the probability of xi is equal to n for each I. Okay, so if all the events are at the same probability, which means that the random variable is uniformly distributed essentially. Okay, so the maximum entropy you can have is log n, and this happens only if the variable is uniformly distributed. Okay. And again, the proof uses some result that we don't really want to go into now, but essentially if you take this formula here and consider that minus will change your, I mean, we can look at it basically, the entropy of X is given by minus the sum of P log P, right? And this is the same as the sum of P log 1 over P. I've taken the minus in, so it's Pi to the minus 1, right?
Okay.
And then we use this result that, again, I said we don't really want to get into, but we can bound this by log 2 of the sum of P 1 over P. And this, of course, is 1. Sorry, is n, because this number is 1, so it's 1 plus 1 plus 1 plus 1, so it's n.
Okay.
So we get log 2n. Okay, and this is the crucial step that uses Jensen's inequality and concave functions and stuff like that. Okay. So of course, like the function has to be concave because otherwise we would not have a properly conducted experiment. Okay, so this actually now becomes an equality if all the probabilities happen with the same probability. Okay, so yeah, so the entropy is maximized when all the probabilities are equal. And of course, this is kind of, now we're trying to measure uncertainty, so we just define the entropy function in general. And now we can think of applying this to the random variables that define cryptosystems like K, M, and C. One associated to the keys, like what's the uncertainty in using a certain key, and certain plaintext, a certain ciphertext, right? Mm-hmm. And of course, the idea is that the more entropy you have, the better for the user and the worse for the attacker.
Yeah.
Yes. So if you take a shift cipher, which is the textbook shift cipher with 26 values on the letters, each of them are the same probability, and you get the h of k is exactly log of 26. Okay? Mm-hmm. And if you consider, so this is not a very high value actually.
Yeah.
If you consider the dumb cryptosystem that we saw before with the unbalanced probabilities, remember that like two plaintexts were probability 1/4 and the other plaintext was probability 1/2 essentially. So what's the entropy in that case of the random variable m? Well, this is going to be exactly minus 1/4 log 2 of 1/4 for the first message, and then minus 1/4 log of 1/4 for the second message, and then minus 1/2 log 1/2 for the third message. Yes, so yeah, so if you do these calculations, this is log base 2, so it's actually even easy because 1/4 is 2 to the negative 2, so you get 1/2 here, plus 1/2 here, plus 1/2 here. Yeah, this is -2, so you get plus 1/2. This is -2, so you get plus 1/2, and this is -1, so you also get plus 1/2. So then you get 3/2. Okay. Notice that this is approximately 0.585. Okay, and this is much smaller than log 3, which is 1.585. And this would be the maximum possible entropy in a crypto system with just 3 plain texts, right? So, so there's that. Okay, so clearly you can see that the entropy here is much smaller, and there's like a lot less uncertainty. And then you can work more with entropies, defining the entropy of conditional entropy if you have a variable condition on another variable, and so on. But we don't have to go into that. Okay, for example, one important. So what you can define. Okay, maybe we can. What we can define is the conditional entropy of x given y, and this is minus. Well, it's going to be a sum of a sum, right? This is the sum from 1 to m on I, and then from 1 to, so this is n, and this is m, of the density of y, yj, density of x given y, xi given yj, times the log of that. Xi given yj. Okay. This is sometimes also called, so this is called conditional entropy, or also equivocation. I think the name equivocation gives it away more than conditional entropy, right? So the equivocation, what does it mean equivocation? That you're making a mistake, that you're thinking about the wrong thing. So if you say send a signal over a noisy channel and then it's distorted, then you define the equivocation to be exactly the entropy of the original signal given what you received. As I said, Shannon was studying a lot. He's a forefather of communication theory as well. So basically, he can measure the amount of uncertainty in a transmission over a noisy channel. And if we use this to model like a secrecy system, like a crypto system, then basically the original signal is the plain text, right? And the received signal is the ciphertext. And you want to see what kind of equivocation you get there, right? What kind of uncertainty you get there. And we apply this idea to cryptography, right? So a large equivocation means that the ciphertext really hides the plain text. And a small equivocation means that it's somewhat easy to recognize the plain text from the ciphertext. Okay. So that's why equivocation kind of plays a role. The word is kind of explanatory. Okay. So the notion of conditional entropy is like a purely probabilistic notion, but when we apply it to cryptography, we apply it in this sense. Another important, so we can look at what's the entropy of C given M, for example, and that's the thing that I just described. But also, we can look at the quantity H of K given C, right? Which is this is obviously called key equivocation, right? This is a different idea. This is the entropy of the key given the ciphertext. So it reveals what is the amount of information given on a certain key, right, given a certain ciphertext. And again, this is an important quantity, right? Because if you are able to extract information from ciphertext and recover the key, this is obviously not good, right? And so actually, we can compute this quantity exactly, and this is in fact corresponding to h of k plus h of m minus h of c. Okay, and again, it's possible to prove this. You can do this. You can then compute this quantity for, again, the dumb crypto system that we had before with the unbalanced messages. And you find that this key equivocation in that case is something like 0.11, which is a very low value. Okay? Which means that just an average ciphertext will tell you with reasonable certainty what key was used. Okay? So we're going to skip the rest of section 4.6, which is a little bit more technical, but you're welcome to read that. And talk a little bit, to conclude, about complexity theory. Which is a big wormhole, and there's a lot to learn there. So obviously, if you have the chance of, and if you're interested of taking a class which contains a little bit more complexity theory, I think it's very interesting. I always found it very interesting. Okay. So what is complexity theory? It's measuring the complexity of mathematical problems. Okay. And of course, in a sense, it's mathematics, but it's also, again, the foundation stone of computer science. So what is a decision problem? I mean, there's a part, right? The very beginning of computer science was born out of mathematics in the 1930s and 40s with Turing, you know, and Shannon and Church and a lot of forefathers that are very famous, and rightly so. So what is a decision problem? This is the fundamental notion. For trying to compute stuff, right? It's important to determine things. So a decision problem is a problem in a formal system that has a yes or no answer. Okay, very simple. So we can model decision problems as be like yes or no. For example, what is the decision problem that is being most recurring in this course so far is prime. Mm-hmm. So prime is a decision problem that asks, given a certain integer, is this prime or not? And the answer is yes or no. Okay. What is a less trivial decision problem, for example? Well, the Diffie-Hellman decision problem, right? The DH. Mm-hmm. The DH is a decision problem that, given g to the a and g to the b, determine whether a certain number h is either g to the c or not. Sorry, g to the ab or not. Okay. Mm-hmm. And again, this is a decision problem. The answer is yes or no. So complexity theory is trying to understand and quantify the difficulty of solving decision problems. And it all started, again, in the 1930s with Turing, and he proved a very important result, that there exists no algorithm to solve the halting problem. You know what the halting problem is? It just asks, given a certain algorithm, will it stop or not?
Oh, okay.
Okay, will it terminate? Eventually, how's the execution? On an arbitrary input. Mm-hmm. Okay. So yes, so it seems trivial, but it's really not. And in fact, he was able to prove that there is not a genetic algorithm that, given a computer problem, is always able to tell whether the algorithm terminates or not. Mm-hmm. If we did that, it would be great. We would solve a lot of problems in computer science. Like if we knew right away when you write a computer program, oh, this is going to terminate or not.
Yeah. And
because it would tell us if there's a bug or not, right? So, as easy as it seems, it's actually crazy to think that we can't even tell for sure whether a certain algorithm will actually terminate or not. Okay? And this is an example of what we say an undecidable problem. Okay, so this problem is actually undecidable because we cannot for sure answer it, right? And then Alonzo Church also proved that a certain problem in the lambda calculus was also undecidable, and therefore there's two problems that are undecidable. They actually are able to prove that are essentially equivalent, and in fact they were able to prove that if you have axiomatic systems right? So Gödel was a mathematician and philosopher. Back in the day, mathematics and philosophy were very close when you look at formal systems and logic, right? And Gödel is the person that formulated, for example, all the axioms, right, of mathematics. And you know what the axiomatic system is, right? You always have to start building from something, right? So you assume, for example, in geometry that two parallel lines never intersect and whatnot. Like you set, so Gödel set up the axioms of the natural numbers,
Okay.
just the natural numbers, right? The zero exists and whatnot. And once you have the axioms for the natural numbers, then you can build the integers on top of that and whatnot, and in respect of the roots, right? So when you set your ground rules, the axioms. But what they figured out is that whenever you have a strong axiomatic system, they always contain some statements that are true but unprovable, impossible to prove. And in fact, there is many undesirable problems in mathematics, and most of them actually have very simple formulations, and yet you cannot determine them, right? So here is another one that is quite famous, which is Faust's correspondence problem. And the idea is to look for correspondences. So suppose that you have a bunch of strings, pairs of strings, S1, T1, S2, T2, let's say SK, TK, where the S's and T's are strings, okay? Strings are just lists of characters, so we're just trying to decide. Again, this was before the bits and everything were invented, right? This is the beginning of computer science. Computer science is basically logic, and then then the bits arrive. So the correspondence problem is asking this: if I have a sequence of pairs of strings, can I find a certain subsequence, right? A certain SI1, TI1, and then SI2, TI2, and then like an SIR, TIR, right? So that if we concatenate that, or such that if we concatenate SI1 and SI2 and SIR, and we concatenate the TI1, TI2, and TIR, then these are equal. Okay? So I have a bunch of different pairs of strings. I have strings of the type S1, S2, S3, and I have strings of the type T1, T2, T3. If I match them in a certain way, can I actually find two equal sequences? But then I've constructed them uniting like different substrings.
Okay.
And again, this has been proved to be undecidable. Okay, so now there is this kind of crazy problems that are relatively easy to formulate, but you don't have an answer for it in general.
Yeah.
And of course, at the opposite end of the spectrum, we have like easy problems. This we kind of already explored, for which there exists. So these are kind of like the hard problems. The easy problems are the ones for which there exist actually quick algorithms to solve. And by quick, we mean polynomial time. So it makes sense now to make a formal difference between these two types of problems. And so we say that we have a class of problems which is class P, which contains problems for which there exists algorithm that answers in polytime. Right, so it makes sense. P is polynomial time. In particular, if the input is length n, we want a polynomial in n number of steps. Okay? So the problems in P can be solved in polynomial time. Okay, then we classify the other problems, and we introduce a class n, NP, but NP is not straightforward as you think non-polynomial. It actually stands for non-deterministic polynomial time. So the class NP is a little bit more subtle. What is in NP then? Non-deterministic means that I am allowed some randomness, right? I'm allowed probabilistic algorithm. So I am allowed even to guess, okay? And so if you have a non-deterministic machine, you can guess or you can use like probabilistic techniques or anything, but you need to be able to verify the answer in polynomial time. Okay, so it's not just the problems. You see, if you define it in a way that is not completely opposite the previous one. So you have some easy problems in P. Yeah? You have some easy problems in P that are the ones that can be actually solved in polynomial time. So there are actually algorithms that spit out your solution in polynomial time. And we've seen some examples already, right? So what is an example of a problem in P? Of a decision problem in P, right? To see, for example, given A and B, right? Decide whether their GCD is greater than 1. So if they have like a non-trivial factor. We can do this with Euclidean algorithm, and you know it takes O(n)³ steps, right? With all the algebra and stuff. We also have the problem of primality, and now we have the AKS test, right? And you know that this runs in kind of like less than O(n)⁷. So it's already pretty slow, right? But from a theoretical point of view, this is a decisional problem which has an algorithm, which outputs yes or no in polynomial time. So these are problems in P, that easy. So you can actually produce the solution in polynomial time. Problems in NP are the ones that can be verified in polynomial time on a non-deterministic machine. Okay? Of course, if you do have a polynomial time algorithm to solve the problem, then you also can verify the solution clearly. But not vice versa. So you may have a way of checking whether the solution is correct or not. Because again, this captures the idea that you can even just guess.
Yeah.
Right? Because if you cannot even check your solution, then the problem has no hope, right?
Yeah.
But this doesn't mean that there is nothing. For example, the undecidable problem of the correspondence problem is in NP. Because given these strings, pairs of strings,
Right.
you don't know how to find a correspondence. But if you want to check, right, you can simply concatenate this. If you have a proposed solution or you want to verify an answer, you can take the strings, concatenate them, and see if they match or not.
Yeah.
So there's a big difference. Between the two, and of course we've seen that one is certainly contained in the other, but what is not clear is whether P is actually equal to NP or not. Because the idea is that, okay, maybe I know how to verify the answer, but I don't know how to produce the answer in polynomial time. But does this really tell me that doesn't exist a polynomial time algorithm to produce this solution? And so this has been an open problem for a long time, and it's one of the millennium problems. So if you are able to solve this, you can win $1 million. And actually the fun thing is that every now and then in the research community pops out a proof that is, I don't know, 40 or 60 pages or something, and it's like claiming that, I don't know, P is equal to NP or P is not equal to NP or something, and there's eventually always a mistake at some point. Okay, so there have been people that have been trying to answer this, and they claim to have a solution, and then their proof was wrong. So, so yeah, this is clearly possibly the most famous open question in mathematics and computer science, whether P is equal to NP. And again, we said one clearly implies the other, but not vice versa. Every P problem is also NP, but we don't know if every NP problem is also P. So this brings us to the idea of measuring the difficulty, right? And clearly the discriminant here seems to be polynomial time. And therefore we can say that the two problems are basically the same. Because look, if two problems are both in P, then there must be a way to reduce one problem from one to the other.
Yeah.
And this is why some time back we talked about reductions. So polynomial time means easy. And so if you have a problem A and you have a polynomial time reduction to problem B, or vice versa, you can take any solver for A and solve B, or vice versa. And therefore the two problems are in the same class.
Yeah.
Okay? And so this is why we then look at reductions between problems. And then this idea was taken to the extreme by a fundamental paper by Cook. This was much later in 1971, where a lot of things were being formalized, which laid the foundation of what we call NP-complete problems. And so the idea is that you're going to reduce to other problems, right? And starting with certain NP-complete starting with certain NP problems, you can reduce to these well-known problems. And one problem here that is always coming out is the SAT problem, which stands for satisfiability, which is again a problem that is really capturing the essence of this topic, right, of mathematics and computer science in the sense of logic. What is the satisfiability problem? If you have a Boolean expression, right? I don't know what your formal logic is. Like, but if Boolean expression contains only ors and ands and nots, okay? A not B, A and B. Then you don't know if there is an assignment of truth values that actually satisfies this expression and makes it true. Is it possible that A and not B implies C and not A or something like this? You take a long expression, given a generic expression, formal expression, you determine whether there is one assignment. Of course, the more variables you have, the more ones and zeros you have, right? And then this becomes quickly infeasible. So the satisfiability problem is hard, right? But again, it's in NP, because once you have, A is true, B is false, C is true, once you have an assignment of truth values, you can immediately check the solution. Right. So it's an NP problem, and in fact, what Cook was able to prove is that this satisfies two properties, that every NP problem reduces to SAT. So SAT is kind of like the mother of NP problems, because you can transform any other problem into a satisfiability problem.
Mm-hmm.
You basically, like, it's complex, but you imagine that what is satisfiability problem? You have like this variable and this other variable, and a variable is like yes or true or false, true or false, true or false. You can formulate your problem, however complex is a problem of true false with a bunch of different logical variables. And second property, if there exists any problem in NP that is not in P.
Can you move that?
Sorry. Then SAT is not in P. So if you can prove that there exists a problem in NP that is also not in P, then SAT is also not in P. So basically, these kind of problems together is what we call NP-complete problems. So they are NP-complete. So basically they are as hard as every other problem in the NP category, right? And then you can reduce every problem to that. And of course now you have SAT, which kind of works as a opener, as like the mother of all NP-complete problems. But then once you reduce, any other problem that has these two properties is also NP-complete. And so what you do is you're able to say you take a problem, P, P is a bad variable. Take a problem A, and then you're able to prove that A reduces to SAT. Then now you have SAT and another problem. And then you do design. Then you have like basically a small portfolio of canonical problems that you know are NP-complete and equivalent to each other. And every time you're studying a new problem, you can look whether you can reduce to SAT or 3D SAT or other problems that graph isomorphism and other stuff, right? That are NP-complete. If you're able to do this, then it's good because you know that your problem is basically at the top of the food chain.
Right.
Okay. So related to this, there is the notion of NP hard, and basically an NP hard problem satisfies the first problem of reducibility without needing to be in NP. Okay, so it's like one, but not necessarily in NP. Okay. So all the NP-complete problems are also NP hard. But not necessarily vice versa. And one example of this is the halting problem, which we said is undecidable. Right? So the halting problem is NP hard, but is not NP complete. Because the halting problem is not NP.
Right.
Okay?
Okay.
It's not NP, you cannot check the solution in polynomial time.
Yeah.
Okay. So basically, I don't want to make it like too formal, but the difference between P and NP hard and NP complete problems is at the basis of complexity theory, and of course complexity is important in cryptography because it determines how secure your system is. And ideally, here is what happens. For example, we've been talking just about decision problems. Let's look at problems that actually, not all of them are decisional problems. Some of them have an actual answer. You can formulate this theory starting from decision problems to problems that have an answer, such as instead rather than yes or no, say find a factor, for example, right? So the integer factorization then becomes an NP problem. Here the answer is not yes or no, but the problem is given a composite number, find a non-trivial factor. So it's kind of like given C, find A that divides C, and A is different from 1 and C. Okay, and this problem is clearly NP. Because if you propose a factor, you can just try to divide and check. So it can be verified in polynomial time. What's another problem is the discrete logarithm factor, or DLP. Right? The discrete logarithm problem, which is given G and H, find X such that G to the X is equal to H. And again, this is an NP problem. So given a candidate solution X, you can always verify that G to the X equal to H or not. Okay, and these are, so these are both NP, and it is not known whether these are going to be NP or not. Okay, at least at the time of the writing of the book. Now we see that things are about to change with quantum computers. Okay, so these problems, for example, that are based on the classical cryptography is based on, are just presumed to be hard, but no one has. So in general, like we don't know of a polynomial time algorithm to solve them. Again, this is all if we forget for a moment about the quantum computers, and this is why it changes so much in the scenario, right? Because then, so the problem of producing a solution is usually not the same as actually determining whether a solution exists. But essentially what we've seen already is that the crypto system is only as secure as the underlying hard problem. Okay, so of course what you really would like to do is to be basing your security on NP-hard problems, for example.
Yeah.
Because if there are NP-hard problems, then you are actually guaranteed that finding a solution is hard. And so of course, there's two things that you need though. You need an NP-hard problem, but also you need a trapdoor.
Mm-hmm.
Again, traditionally. Then there is stuff that we do nowadays that actually doesn't use trapdoors, but that is like one step further. Okay? And so it's not obvious how to do this. And what you can do is, because you do need a trapdoor, then you kind of like use a subset of special cases of the problem, not the problem in general, and then you may lose your hardness if you just use some selected instances. And here is an example that is very intuitive. There is a crypto system by Merkel and Hellman, which is usually known as knapsack or subset sum, which is very interesting. And the subset sum problem is essentially asking this: if you have a bunch of positive integers, a1, an, and a target number s, can you find a subset ai1, ai whatever they call it, t, such that ai1 plus ait is equal to s. Right. If I give you a bunch of numbers, you need a second. If I give you a bunch of integers and a target number sum, can you find a combination of them that sums to that?
Okay.
Right? It's a very, very intuitive problem. It's beautiful because it's very easy to imagine. I give you like 1, 3, 5, 10,000. Of course, this depends on the size of the integers and then how many we have. But in general, this problem is NP complete, in fact. And I'm not sure exactly because I forget. But this is kind of what I work in anyway. So it's, I don't remember exactly what the subset sum reduces to, if it reduces to SAT or one of the other pillars anyway, but there is a proof. Always there is a proof of NP completeness because you have to reduce to one of the other NP complete problems to show that your problem is NP complete. Remember, the NP complete implies also the hardness. It implies NP hard.
Yes.
So that's good. So if you have an NP complete problem, this is great.
Mm-hmm.
Once you have NP complete problems, every new NP complete problem that you have, you can use to prove new NP complete problems.
Yeah.
So this is kind of what happened in my area, where basically the subset sum is a very generic formulation. You have a bunch of elements that sum to a certain target. Can you decide whether a subset of these elements sums to that? And the Merkel-Hellman knapsack crypto system, which I think and hope we will have the chance to see in practice, is basically based on this idea that you have like a secret combination of them that you know and the attacker doesn't know.
Yeah.
And then, of course, the security of the crypto system is based on finding this combination. But it does use not the generic formulation, but a bunch of special cases. right? For example, if your sequence is increasing, strictly increasing,
Right.
that every next integer is bigger than the previous one, then the problem is intuitively easier to decide, right? And therefore, you kind of lose some hardness. So what happened is that they claimed, because they needed a trapdoor, and so they only used certain special cases of the problem, but it turned out that these are actually much easier to solve than the general case. Okay, and so was kind of like stuck in there. And of course, yes, even if you have like a certain collection of problems that is NP-hard, you don't know actually that every problem in there is NP-hard. So there is basically NP-hard measures the worst case, but you're concerned about the average case instead.
Right.
Okay, so we should see later these like new generation publicly cryptographic systems that are based on hard problems, right? And in particular, we will see two things. Very roughly speaking, there is one area that is called lattices, which is a mathematical structure, kind of like a reticulate, you know, like so. A lattice is an object of this type, like this. Yes, where all the vertices are like integers and stuff.
Yeah.
And you have vectors here, you have vectors here, you have vectors. So what happens if I now give you a vector like this, and I ask you to determine what is the closest point in the lattice to this?
Okay.
Yeah, and this is what is called a CVP problem, closest vector problem. And of course, what you can imagine, we will see this in more detail, but just as an introduction, the idea is clever, and it's, yes, I take a lattice which is structured, I take a point in the lattice, and I disturb it a little bit so I get out of the lattice. And my secret is going to be kind of like, I know where this point was coming from,
Right.
but now you're out of the lattice, and you cannot tell which one is the closest point. Of course, this is in 2 dimensions, right? I think many dimensions. So CVP is an NP-hard problem, and lattice-based cryptography essentially kind of revolves around either CVP or some problem is like modification of CVP or anyway reduces to CVP. And the other stuff that we will see is on linear codes, which is a different mathematical structure. Linear codes are used for communications. When you transmit a certain message, what you do is you have a message, and then you add some redundancy to the message, so that essentially, if some error occurs in the communication, you're able to correct it. Yes?
Okay.
This is actual communication theory, because when you communicate, for example, with satellite, and you get images from Mars or something, right? And of course, you can imagine, it can happen that this get corrupted, right? So you still want to be able to like recover and correct the image.
Yeah.
Another very interesting example of this is actually QR codes.
Okay.
You know QR codes, right? You scan the code. And if you notice QR codes, when you scan them, you want to be able to get to the correct URL.
Right.
Doesn't matter if you scan it like in this way or this way or this way, and they have a very high correction capability, in fact. One element, one game that I like to do with like high school students and the kids in school when I talk about that is just take a QR code, like big, and print it on a piece of paper. And then what you can do is like a rip off, like one corner of it, for example, or just like start coloring black some parts that are white, and you can see that up to a certain point, it can still read it correctly.
Yeah.
Now, of course, a QR code is a pictorial representation, but in general, a linear code just works on like strings of bits, right? Because that's just converted to it.
Right.
And the idea is that you have a certain way of encoding information, and you add some redundancy. And then if you have some errors in communication, like you flip some of the bits, then up to a certain threshold, you can still correct and get the correct message.
Yeah. Okay.
And again, the idea here is a different type of problem, which is called SDP, or syndrome decoding problem, which is kind of what I already told you. If I give you a syndrome, which is like this output of the communication, and it's got some errors on it, are you able to decode this to correct the errors?
Able to recover the...
Yeah, to recover the correct message. And so the idea is kind of similar. If you see, this problem is also NP complete. This is actually NP complete. And it's just a good problem to base cryptography on, right? And you're kind of gonna do the same thing. You have your plain text, and you hide it by like artificially like making some errors, and then an attacker is required to correct these errors that he doesn't know how to compute.
Yeah.
Correct. So this is kind of the idea. We're gonna use now really hard problems. And of course, back in the days of RSA and stuff, it's like, oh, there's this new thing, it's called public key cryptography, and we can do it with this like very intuitive problem, factoring, you know.
Yeah.
And that was like at the beginning, and now we're sharpening our tools.
Yeah.
We're actually using NP-complete problems to base our cryptography, because it gives us more guarantees, right? And so this is what we're going to be looking at next.
Cool.
Okay.
Yeah.
Yes. So this was the summary that I wanted to do today, and yes, we start next week with the new stuff. Hopefully, it's going to be exciting. Okay. Excellent.